So I'm told that we can start. Let's continue with the last talk of the day. And it's my pleasure to introduce Souvik from Christ University, Bangalore. Will be speaking to us about representations of Hamiltonian vector fields on a torus.
So about some joint work with Ishwar Rao, and which is about representations of Hamiltonian vector fields on a torus. So let me start with a brief motivation and background. So this is a very important class of infinite dimensional simple Lie algebra, which came out of Karta's work, and which usually appear in the study of vector fields on manifolds, known manifolds. And classically, in the very first time, actually, when it was done, and they were categorized usually into 4 classes of vector fields, and with formal power series coefficients, that is when it was done for the first time. And there are these 4 series: W type, S type, H type, and K type. That is the Witt algebras, divergence-free algebras, Hamiltonian algebras, and these contact algebras. So in my talk today, I will be focusing on this Hamiltonian type mainly. So these representations were initially studied by Rudakov. It is in the 1970s. It was initially studied when he considered these over formal power series with formal power series coefficients. Then actually around in the 1980s, Shane actually studied the graded representations of these Karta type Lie algebras, but now with polynomial coefficients. So no longer with formal power series coefficients, but with polynomial coefficients by something which he calls this very complicated procedure of these mixed products. Okay. And these Lie algebras were there for a long time. Notably, they appear actually in Kak's famous conjecture of this classification of graded simple Lie algebras having finite growth, which was finally proved by Olivier Mathieu. Okay. So then actually, so a natural thing to do is to not only restrict to polynomial coefficients, take lower polynomial coefficient, and then develop the representation theory. So this was first done by from the physics side by Larsen, who actually came from a conformal field theory background, and he constructed a reasonably big class of these graded representations for the W type Lie algebras with lower polynomial coefficients. And this particular W type Lie algebra can be also has a nice geometric interpretation. It can be realized as the Lie algebra of complex polynomial vector fields on a n-dimensional torus. And algebraically, it can be defined like this. So it is like this some notation. So these di's are like the degree derivations, and this is some notation u r t to the power r di. So it is basically you can think of it as a module of with a free rank. It's a free module of rank n over the LoRa polynomial ring in n variables with basis d1, d2, dn. So it's basically like that. And this is the Lie bracket structure. This is the inner product notation. So this is algebra, and it is well known actually that it is connected to a very well known algebraic object, which is the space of this derivation algebra of the LoRa polynomial algebra. Okay, so it has a nice geometrical interpretation as well as a algebraic way to look at it. And important thing about this actually, so these are all n-dimensional. So let me just note this point. So if you take Rf, it is Zn graded, and if you take dimension, it is capital N for all R, Z. Okay. So this is about W type. It has been studied. Lots of work has been done on this. So today, as I said, I will be mostly considering the H type. So before that, briefly, I will define what is the S type, divergence-free vector fields. It is interested. So it is just, you take DUR, the previous notation, inner product of UR is 0. Inner product means summation UI Ri. So this is the divergence-free vector fields. This is the S type. A lot of work also has been done here, quite a few. And here the graded components, at least the non-zero graded components are, here it is n minus 1 if r not equal to 0, and it is n when r equal to 0. So it is quite similar, not exactly, but it's very quite close to W type. So there are very, very subtle differences. So today I will be working with this Hamiltonian type Lie algebras, and they are known to exist. Obviously, it's Hamiltonian type, so it is known to exist only when this in the even dimension, and they are defined using this Lie derivative with respect to this differential form, this symplectic 2 form. And the definition is like this. So it's the vanishing of this form with respect to this derivative. So this is the Hamiltonian Lie algebra. This is the geometric description, but one can also give a nice algebraic description of this Hamiltonian Lie algebra. So this is the description d r bar r, where this is the r bar. So what basically d u r was there. So instead of that, I am taking r bar. So that r bar is looking here a little bit odd, maybe rn to rn plus 2n like that, but it is basically this thing. So J is the usual matrix that comes actually when we deal with this symplectic Lie algebra. So you just take J, this n cross n matrix, and then multiply with this R, you exactly get this. Okay. R bar has 2n components. Oh, okay, it is Rn plus 1. Right. It will start from Rn plus 1. Thank you. So R bar, it would start, it is a typo there. So it is R2n, and from there it is going minus R1 to minus Rn. This is the correct one. This is a typo there. Okay. Yeah, Z2n. Yeah. So I am, for the entire talk, I will now take capital N is equal to 2n. Okay. So this is the thing. And one of the notable differences from this Wn and Sn, that it's Zn graded, okay, but the non-zero graded components are one-dimensional. So there is a huge shift from such a big dimension. It has chopped up a substantial part. So this is one-dimensional, the non-zero graded components. Okay. Now we want to study its representation theory. So I will take an SPN module, the symplectic Lie algebra, and this is my notation. I will write this notation because time and again I will use this. Beta V is V tensor An. An is the Laurent polynomial algebra in n variables. Okay, so then actually one can give an action of Hn on this loop actually like this. This is the action. So Hr is acting like this. This is the inner product that I told you. And here R bar transpose, what do I mean by this? So this R is an element in Zn, and you take U is an element in Zn, but when you take its transpose, it becomes a row vector. So this is a n cross n1 matrix. This is a 1 cross n matrix. So when you multiply, you get a n cross n matrix, and this part is called, these modules are called Stein-Larsen modules. This is the usual standard terminology. And first thing to observe that this is R bar transpose is an element of the symplectic Lie algebra. So this action is well defined. Okay, this action is well defined. And second thing, of course, it's a Zn graded. We can see it's an infinite dimensional module, Zn graded. And Zn graded, it's simple observation, are finite dimensional if and only V is finite dimensional, because these are the graded components. These have to be finite dimensional only if and only V is finite dimensional. Okay. So now what type of problems are we interested in? So we have this functor from the category of SPN modules to the category of Zn graded Hn modules. That is what we saw in the previous slide, that we have to start with any module, SPN module V, and take V tensor An, we can give it a Hn module structure. So the problem, this was posed actually quite recently by these 4 people, Pen, Sheng, Tao, and Zhao actually in their paper, that what they actually asked is they want to understand this functor, roughly speaking, corresponding to irreducible SPN modules. What happens when V is irreducible? How do the functor behave? How will V tensor An behave, and so on? So let's start with the first obvious question. Does this functor preserve irreducibility? So what do you mean by that? That if V is a irreducible module, SPN module, is V tensor An irreducible or not? Okay. So one of the main problems with working with this, rather than for this Wn and Sn is that the non-zero graded components of Hn are too thin. As I told, they are only one-dimensional. So that makes a it becomes very difficult actually to work with it. That is one of the main constraints actually to answer this question. So for this actually we needed some characterization lemma. So if you have an irreducible SPN module, so this is an submodule, okay? So this is the first thing we can construct this space. This turns out to be a submodule. And this submodule will be equal to the whole module if and only if V is a fundamental representation or the trivial representation. So this is a nice characterization of the fundamental or the trivial representation. And this is very, very useful when we are trying to answer this question. Yes? My too thin means that this here actually for Wn and Sn, the Zn graded components, one was n-dimensional, non-zero I mean, non-zero Zn graded components are one-dimensional and n minus one-dimensional. Okay, in this case it is just one-dimensional. So that was what I mean. Okay. Okay, I have to write down the calculation. Some specific form it will come, but I will tell you something. Some result will come. I will tell you at that time. We will see that one result is that it actually spans the whole space. If you take R bar transpose and take vary R over Zn, that will span entire SPN. Second power, correct. Yes. Okay. So this is the final. We using that characterization lemma, we could prove this, that if you start with an irreducible module and beta is in Cn, that beta thing is coming. This is irreducible if actually it is not a fundamental representation or a trivial representation. So this theorem actually gives a sufficient condition for the irreducibility of that V tensor A, and it's not a necessary and sufficient. It is giving you a sufficient condition. So now, these are the modules which we need to understand. So this fundamental modules are the trivial modules. So let us start with the simplest case. What happens to this V tensor An where V is the trivial representation of SPN? So what we could show that this is irreducible if beta is not in Zn. So corresponding to the trivial representation, when you construct these Shane-Larsen modules, V tensor An, this is irreducible only if beta is not in Zn. What happens if beta in Zn? Then you get these two irreducible submodules. Okay, and note that for beta in Zn, this is so since it is C, you can identify with An only. And these are the two irreducible submodules. So you can write it actually, this sum, where these two are irreducible submodules. So we sort of understand this quite well when V is the trivial representation, what is the functor. So what we got actually, so the Shane-Larsen functor takes any irreducible SPN module to an indecomposable Zn module. This is indecomposable unless what I showed you, V is trivial and beta is in Zn. Unless this SPN module is a trivial representation and beta is in Zn, this is always an indecomposable module whenever we start with an irreducible module. And of course, what I told you, beta is in Zn, then of course, corresponding to the trivial module, it's completely reducible with exactly two irreducible summands, what I just showed in the previous slide. Okay, so we sort of understand this functor. So to address the rest of the question, we need to understand the submodule structure for the fundamental representations corresponding to the, so when I take the functor, when I take here in case of V, I take V omega P, P lying between 1 to n, what will happen to this? So that is what I want to understand. So a very, very big problem in this. So Professor Feijin has talked a lot about fundamental representations of SLN. SLN, the advantage we have, the fundamental representations are very explicit. They are just wedge products, very nice wedge products, very explicit realization. Here the problem is, except for the first fundamental representation, none of the realizations are very simple or explicit. So let me tell you what are the fundamental modules first. So first fundamental representation is the usual one, the matrix multiplication. Now the wedge product, unfortunately, is not irreducible over the symplectic Lie algebra. So we have this contraction map. This is the two contraction. This is the inner product I told you. This is just a contraction map. You think about like this. So this Vi hat means these two terms are omitted from the expression. So then this is a onto module homomorphism. And the fundamental representations are given by the kernel of this contraction map. Okay. So you can very well understand it's so much complicated to work. It's not a very nice explicit realization. So that is a major challenge actually with working with the Hamiltonian, because these kind of things come into the picture. Okay. So what we did, we tried to construct submodules inside those the Larsen module corresponding to the fundamental module. So one of the submodules we constructed like this. So it's a Zn graded module. It's enough to define it on the any graded component. So what is the definition? So this on the kth graded component, this is the definition. K plus beta bar transpose acting on the this wedge product, where this wedge product is taken from the fundamental representation. Okay. This is well defined. As I said, this thing is in SPN, so this is well defined. Okay. So this is another realization of this actually. This is very useful. So what we do, we take K plus beta, wedge it with all these things, P minus 1, and this thing need not lie in the fundamental representation, so we need to intersect with it. Okay. And okay, so it's an irreducible submodule. Okay, important thing is that it's not only a submodule, it's an irreducible submodule, and not only that, it is the unique non-trivial irreducible submodule. Okay, inside that there are no other non-trivial irreducible submodules apart from this one. So I will just make a note of this realization. It will come in handy later. So I will write the kth graded component. Okay. So due to that, we call it the minimal module. There are other strong reasons for calling it, but for the time being, this is the reason. So we call it the minimal module for this Larsen module. Okay. So then we constructed some other modules. This is simply, so we are now taking all those elements. So it is the kth graded component, all those elements which are killed by these type of vectors. Okay. So this is another example of so it is a submodule of this, and any proper submodule is contained in this. Okay. So if you take any proper submodule of this V omega P tensor An, it has to be contained in this one. Okay. What square? No. That will be 0. So you have to take only the first one. Yeah. So that is reason, and that is the reason we call this as the maximal submodule or the maximal module for this Larsen module. Okay. So there are two classes of modules we have defined, the minimal module and the maximal module. Okay. And then finally, and not only that, interesting thing is that this turns out to be indecomposable. So we got a non-trivial example of an indecomposable module, which is almost always not irreducible. Okay. So now we define some other things. So this is sort of influence from chain complexes, so chain maps. So now I am taking it on the full wedge product, full exterior product. So it is going from P plus 1 degree to P degree, okay, one contraction. And so this is a HN module homomorphism. So obviously its image will form a HN submodule of this Larsen module. Okay. Now, again, as I said, we need to, since I want Larsen modules over the fundamental representation, I need to intersect this thing with the fundamental representation, because this thing need not lie in the fundamental representation. It's just an element of the wedge product. So this is, and we call this as the intermediate module, okay, for this. And this also turns out to be indecomposable. So this is, yes. it can happen. I will tell you. At one case only it will happen. Otherwise, it won't ever happen. Okay. So this is the inclusion between all the modules that I talked about: minimal, intermediate, maximal, and the full module. And what happens when this P is equal to 1, that means when you are working with the first fundamental module, the intermediate module coincides with the maximal module. Okay. And when you are working with the nth fundamental module, that intermediate module coincides with the minimal module. So these are two cases that happen. These are P equal to 1 and P equal to n. For P strictly lying between 1 to n, this will never happen. This will be strict inclusions. Okay. And if P is equal to n equal to 1, then exactly the question that you are asking, all of these concepts, it is irreducible over H2 because I have taken n equal to 2n. So n equal to 1 means n equal to 2. And H2 is actually, if you put S2, H2 and S2 are same actually. S2, what I defined here, and Hamiltonian, what I defined here, for n equal to 2, they are same. So only for that case, actually, specific case, all these things coincide. Otherwise, it's not. So what I get from, in fact, what I wrote down is a Jordan-Holder series. Really speaking, it's a Jordan-Holder series, what I wrote down. So when P strictly lying between 1 to n, it will have length 4 up to trivial modules. And when P is 1 or P is n, it will have length 3 up to trivial modules. And when P and n equal to 1, it will have length 2 up to trivial modules. So, and P equal to 0, we have also seen it is length 2 only. So they admit Jordan-Holder series of length at most 4 up to trivial modules. Okay, so this is structure. Now I want to sort of get into some geometric connection. So these are this is just end now. Module of tensor fields, this is defined with a full wedge product you take, and the P differential forms you can interpret actually like this. There is a correspondence. And then you can define this map, which I defined. You see this minimal module description is sort of matching there, but there I am taking on the entire wedge product. So these modules formed these two complexes. So Tn beta was the map that I defined for the intermediate module. Okay. So this one is increasing and this one is decreasing map. That was one contraction map and this one is the increasing map. And both of them are complex small maps in the sense that their compositions are 0 consecutive compositions. And so their kernels and image naturally give rise to submodules. And more precisely, this first complex that I defined is actually a DRAM complex. So finally, we can compute the DRAM cohomology and homology, and if beta is not in Zn, they vanish. And if beta is in Zn, they are given by this trivial representation of this dimension. So finally, just you take the composition of those two maps that I just showed you. So this composition, so if you take composition, one is increasing, one is decreasing, you see, you will go from same space, this space to this space. And this is a nilpotent module homomorphisms. That means of nilpotency 2, that means it's a complex HN module map. And so the minimal module, intermediate module, and maximal module, all the three modules that I have defined can be actually realized by restricting the kernels of these complex maps to the fundamental module. So this is the geometric picture. So now let me get down to the references. So this is whatever results I told is from this paper. Then this is the paper where they asked this question. And this is the initial paper of Larson, where he considered these modules over Laurent polynomial algebras, this Witt type algebras. And this is the paper of Shen, where he's considered this mixed product technique. And this is the initial paper, very first paper on this area by Rudakov. So I think I will stop here. Thank you for your attention.
Thank you for the nice talk. We have time for questions and comments. Could you please go back to slide number 14 about the sequence of containment? Oh, maybe one more. Yes. So like having this chain of containments of indecomposable modules that you have, particularly with the observation that max and min may coincide.
But the max and min will only coincide for H2, otherwise it will never do.
That's right. So it's a possibility, but other than that, it never coincides. So that naturally raises the question that, like, do you know how far min and max are? Is there any explicit computation of how far they are with respect to their dimension? Or
So you see, first of all, I didn't tell the entire paper. These are actually all the submodules up to trivial modules of this. Whatever you see here on this slide, these are all possible submodules of this.
But I think my question is somewhat. I'm not saying that if there are other submodules. I'm just wondering, like,
dimensions.
Exactly.
So
can you decide
by
how
this
far?
quotient?
Exactly. Can you decide how far they are from each
Right.
other?
Yes, one can give maps actually. This dimension may be tough because this thing actually creates a lot of trouble. But it might be possible to identify the module. See, dimensions computing here also is tough. But it might be, I think it is possible to identify the module, because actually what you asked, actually, we actually did in most cases. We computed the kernel by image. That is the homology. We did all those cases. That I didn't present. But what you are asking actually is basically that question. But computing explicitly a dimension may be very hard combinatorial problem. Yeah.
Thank you.
Yes. If you remove the Cartan, I don't know. Obviously, that is still a Lie algebra, because this Hn is actually a semi-direct sum of those two. Like you can take this. Okay. So it is actually a semi-direct sum of this one and the degree derivations. This Hamiltonian. So when you remove the Cartan, of course, the problem becomes much more complex, whether it is because you can't separate the vectors into weight spaces. But yeah, one can try that problem. Yeah. We expect it still, it will be reducible. T, what is T? No, I developed WSHK. Yeah. Yeah. K, there is not much theories there. K actually, case is fully unexplored. W type, lot of work has been done. S type work is going on. Still quite a bit of work. Hamiltonian, not much only. I think this 1 or 2 papers only. Yeah. Which is the group? Oh, the algebra, Lie algebra. Yes, of course. Like for W type, you will get GLN. And for S type, you will get SLN. And for K type, we don't know. I haven't seen any such interpretation. That comes under that comes from a very different perspective, not under involution, as far as I know. Yeah.
Any further questions or comments? That is no longer the case. Then let's thank the speaker.